Foundational computer science rests on a specific observation. Immense computational power does not require complex individual mechanisms. Instead, it arises from the highly structured organization of simple rules. Alan Turing demonstrated that a minimal set of elementary operations is sufficient to execute any computable process. Turing's proof of computational completeness relies on the repeated application of those simple rules within an organized, state-transitioning structure. Claude Shannon reached a similar, parallel conclusion when looking at the foundations of digital circuitry. Shannon proved functional completeness, showing that any Boolean function can be constructed from a small logical basis, such as a simple NAND gate. The shared principle is that expressive power is an emergent property of organization, rather than an inherent trait of isolated complex components. Modern artificial intelligence moved away from this principle, opting instead for massive, continuous parameter spaces. Contemporary deep neural networks operate by optimizing millions of numerical weights using continuous floating-point mathematics. Crunching these dense matrices requires significant computational overhead, driving the high energy demands of current hardware. This raises a question of efficiency. Is the continuous numerical parameter actually the most effective building block for intelligence? We are exploring an architecture that replaces continuous numerical optimization with the structural reorganization of discrete, learnable logic gates. To implement this change, we must examine the foundational unit of modern AI, the classical artificial neuron. In the standard model, output y is a function of weights w times input x plus a bias b. During training, numerical weights and biases change, but the mathematical operation itself remains fixed. The fundamental computational rule remains a design choice, rather than discovered logic. The alternative is a parameterized logical operator, defined as y equals g theta of x. With this operator, the behavior of the logical transformation itself evolves. The system determines which specific logical rule best explains the data it encounters. By making the operation learnable, knowledge is no longer stored purely in parameters. The logic of the system emerges as part of the learning process. Traditional binary logic recognizes only two possible states, 0 and 1. Strict binary logic is limited in cognitive tasks because it cannot represent a decision that is currently undetermined or only partially resolved. This architecture utilizes a ternary computational system, adding a third value, 2. The value 2 is an active computational state, not a simple null or unknown placeholder. It represents a resolved state in its own right, functioning as a contextual selector, a transition between states, or a way to hold a structural ambiguity. This third state moves logic beyond simple truth evaluation and into a dynamic mechanism for resolving constraints. In classical neural networks, the forward pass destroys information. You cannot mathematically work backward from an output to find the exact input that created it. A single ternary logic gate cannot solve this alone. If a gate maps multiple inputs to the same output, information is still lost. Reversibility here is an emergent property of how gates are organized into assemblies. This is achieved by arranging 3 ternary gates in a cyclic topology. In this loop, the first input feeds the second feeds the third, which then feeds back into the first, creating a circular constraint. Because each gate in the cycle depends on the others, the system cannot reach a stable state unless all 3 satisfy their local logic simultaneously. This forces the assembly to preserve complementary traces of the computation. This mutual satisfaction enables bidirectional inference. If the system is given a final output, it can resolve the internal gates backward to identify the specific input combination required to satisfy that cycle. For machine learning, the question is how a system learns without continuous parameters to optimize. Standard learning requires a global loss function, where a single error signal is pushed backward across the entire network. This model relies instead on local, distributed coherence. Each ternary gate evaluates whether its current logical operation increases the consistency of its immediate neighbors. Error is no longer a numerical quantity to be minimized. It is a localized structural signal that triggers a reorganization of the gate's logic. Complexity arises as these resolved assemblies link together. When one cluster achieves coherence, it provides a stable logical anchor for the next, allowing a wave of resolution to propagate until the entire system reaches a globally consistent configuration. Intelligence in this model is the resulting state of that network, an organic configuration where millions of local logical rules satisfy one another simultaneously. Moving knowledge from parameter matrices into structural logic has immediate hardware benefits. Inference in these cyclic assemblies requires only simple bitwise operations, removing the need for power-hungry floating-point multipliers. By replacing matrix math with discrete logic, each decision requires only a few clock cycles per gate. This approach can reduce the energy consumption per logical decision by 2 to 3 orders of magnitude compared to standard deep networks. There is also the benefit of interpretability. A network built on explicit logical operators allows for the isolation of specific constraints. While massive emergent systems are never simple to map, a discrete logic architecture provides a structurally intelligible substrate where specific inference paths can be mapped and audited. The ternary logic architecture generalizes the core definition of a computational unit. This comparison matrix highlights the shift from fixed algebraic options to adaptive logical operations and distributed coherence. The classical artificial neuron is a specialized case within a broader universe of operators that are capable of modifying their own internal logic. Turing and Shannon showed us that complexity emerges from the interaction of simple elements. Artificial intelligence does not require increasingly massive numbers to crunch, but rather simple mechanisms that can learn the very logic connecting them together.